Ladies and gentlemen, things are about to get complex here in the complex plane. And we've got Mr. Hendrickson. I love you.
What up? Love you.
And Mr. Klein. What's up?
What's up?
All right. We're hanging out. We're masked up, you know. Masked up, vaxxed up. That's good. I like that, you know. But we're within that 2-week period, you know what I'm saying? So not CDC approved yet. All right, let's hop to it, children. Let's hop to it. We've got Jean Robert Argand. He was a real dude. See, he's right over there. They never smile in the old pictures. They didn't know how to smile yet. So that was invented in 1807. You see, he was 1806. I don't know if that was birth or death, but whatever. All right, complex numbers are the form A plus BI, right? Z equals A plus BI. Some may use X plus YI. Weird people do that. Our electronic book uses that, but the majority of people are going to use A plus BI, all right? And it can be graphed on what would look like your normal XY coordinate plane, but the Argand diagrams. I hope I'm pronouncing his name right. I've actually never heard of this guy. All right. So we're going to label our axes here on the complex plane. The horizontal axis, that's our real axis. That's where we keep it real, okay? And then the vertical axis, which is normally our y-axis, that's our imaginary axis, all right? Lovely, wonderful, fantastic. So let's just say I'm going to go ahead and let's say we've got the point 3 plus 4i. That would be something like this guy right here. We'd go over 3 in the real direction. We'd go up 4 in the imaginary direction, and boom, there we go. We end up getting ourselves this lovely little right triangle action going on here. That's going to be our A, our B, and then this would be our R, okay? Whew, that's good stuff. So let's get some formulas out of this. There's 4 good ones here. We've got our little Pythag looking formula, a squared plus b squared equals r squared, in this case our radius squared. Then our angle of rotation, theta, is equal to the tangent inverse of the opposite, which would be b over the adjacent, which would be a. And then much like our when we're getting tricky with it, okay, a, that's going to equal our cosine theta, or rather our polar coordinates, very familiar there. And then b is going to be our sine theta. Oh, these are all wonderful things here. You know, this is great stuff. I love it. Fantastic. So pop them formulas down. We've got our real, maybe I could have wrote that there. We got our imaginary. All wonderful stuff. I think it's time to graph it. Now, the first example we almost already did, but it's a little bit of a change there. We got z equals -3 plus 4i. So we're going -3 in the real direction, and then we're going +4 in the imaginary direction. And there we are. We've got ourselves, whoop, boom. I like it. Fantastic. Now, the radius, remember we called it the radius earlier. The radius is called the magnitude. That's what we're generally going to refer to it as, the magnitude. We've got other names for it as well, of course. Modulus. Woo! That's good stuff. All right, so we got z, and we're going to denote that magnitude. It's going to look like absolute value bars. Sometimes you'll see it with just 1 around them. Other times you'll see it with 2. They are no different. They're just different notations, different books. I don't know. People like to do things differently. All right. Now, why do you think we wrote down that a squared plus b squared equals r squared? Boom. This is the case right here. We'd have our a squared plus b squared. Square root of that gives us our magnitude. Awesome. Another way you could write that is the absolute value of z, or the magnitude of z, is equal to the square root of r squared. Okay? So if you know what r squared is, square root that gives you your magnitude. If you know the a plus bi, if you know the coordinates, we can do Pythagorean Theorem with that, square root it, boom, there's our magnitude. Awesome. Fantastic. So we've got a graph, -3, 4, going up. We're cruising. We're cruising here. All right, let's graph some more. So we'll do A. I'll do that one in green for now, and then we'll switch colors. So we've got, it says then find its absolute value, right? Or magnitude. So I'd go 2 in the real direction and 5 in the imaginary direction. That lands me right there. So what's my magnitude here? Whoa, that was a little wobbly there. Still a little wobbly. I don't care. Whatever. All right. So I would use essentially Pythagorean Theorem here. So I'm going to do 2 squared plus 5 squared in the square root. And I'm not even worried about it being negative or positive when I'm dealing with the a and the b because I'm squaring it. So it's going to end up positive, right? So that's going to be 4 plus 25. That's going to be square root of 29. There's my absolute value, my magnitude of the first one. Now let's go with, I'll go purple. Purple's a lovely color. You like purple, Mr. Henriksen?
It's actually one of my favorite colors.
One of your faves. I do like it. It comes up quite nice here on my OneNote software. Thanks, Microsoft. All right, shout out. Actually, now that I look at this problem, I'm going to go with red because it's going to show up better for where this one's graphed. But then we're going to go back. I'm going to go right back to purple. I promise.
Okay.
All right. So for B, we have 6i. So that's 0 in the real direction, and then up 6 in the imaginary. So I'm really right up here. Boom. Now you can see why I decided to go red, not purple, because that purple is going to blend in a little too much. All right. So for my absolute value or magnitude, it's going to be 0 squared plus 6 squared. So that's going to be the square root of 36, which is just 6 as my magnitude on that one. I love it. Ah, this is just wonderfully fantastic. All righty. Now, back to that purple. I'm going to go 4 in the real direction. That's the horizontal. To the left. To the left, I believe, was that Rihanna or Beyonce? Beyonce. Thank you. I said Rihanna in one video, and a student emailed me to correct me, but it was already set in stone. All right. So we got -4, and then we're going to go down 1 in the imaginary, so I end up right here. Boom. And now I want to find that magnitude. I've got 4 squared. Again, I'm not even worrying about those negatives because when I square them, they become positive. So why deal with it if I don't have to deal with it? You know what I'm saying? So that's 16 plus 1. That's the square root of 17. We are all Gucci. Love it. Good stuff. Rocking and rolling. Woo! Woo! Forgot to put it, I like some of those, like, add a couple arrows on there, Pop them on there. Boom. Love it. All right, let's keep rolling. All right, so we're going to convert a complex number between rectangular form and polar form. Pending certain forms are more useful for certain calculations. You're going to find that polar form is very advantageous later on here in this lesson and in the next lesson. But for now, for rectangular form, that is our A plus BI, right? Cool, awesome, fantastic. Now I want to label a couple things here in the context of more of like a triangle-looking guy here. So this is going to be my A. This would be a length of B. And then over here I'd have my R, my radius here. And then I'd have my central angle of theta. Okay, so for polar form, we're going to be involving our cosine and our sine for our x and y coordinates, respectively. So cosine of theta, as we know, our x coordinate would be our cosine theta, and our y would be our sine theta. And the same will hold here, except for now, for A, we'd have our, there we go, A equals our cosine theta. Awesome. We just apply that same exact concept there. And we know that B, that's like our y, would be our sine theta. Awesome. Cool. So what we end up with here is our cosine theta plus we have our sine theta, but then don't forget about that I there because it's A plus BI. So the B is our sine theta, and then we have the I afterwards. Now this thing says collapse. So we can actually simplify this. Now I want you to look. We've got 2 R's there, right? We can actually take out a GCF of R. I'm going to change colors for this here. So I'd have R coming out. I'm left with cosine of theta plus sine theta I. So the way we can shorthand write this is R cis theta. Okay? Nice and condensed. That theta is going to be the same angle, right? The cosine is the C, the sign is the S, and then that I is in there as well. So we have R, cis, theta. Our online book doesn't usually use this form very often, but we are going to use it. It's quite convenient. You know, I like writing things short. Like when I don't have time to say Pythagorean Theorem, I just say Pythag, because that's hip. That's what we use when we're doing math on the streets. So, you know, just, you know, street talk. All right. Convert to polar form. Graphing on these can help. It does help to get a visual representation. So I would highly suggest drawing it up. So I'm going to do that. I'm going to draw it up. So I have 8 in the real direction and then negative 8 root 3 in the imaginary direction. And I'm going to look at this as like a right triangle here. 8 root 3. And oh my goodness, this certainly looks like a 30, 60, 90 triangle. Does it not? I do believe it does. So we've got ourselves a 60-degree reference or a pi over 3 reference right here. If that's 8 root 3, this is going to be 16 then. And that's a negative 8 root 3. All right, did a quick pause there. There's a little sync noise, you know, common space problems, hashtag. All right, so I noticed that this was a 30, 60, 90 triangle because of the 8 and the 8 root 3, right? If I didn't notice that, I could have done Pythagorean Theorem to find my radius there, the 16, but I remember math, and that's helpful. So remember math, children. All right, I got that pi over 3 reference. Now we're going to make our conversions here, right? So for this one, my R, I already have, look at that, I already have this. So Z is equal to R, which is going to be 16. And then what is my angle going to be here? What is that theta going to be? That theta is going to be, well, the whole angle of rotation.
Thank you, sir.
Hey, thank you. Ooh,
I saw them.
Raider Way prizes, ladies and gentlemen. I got to make some deliveries. All right. So we got that whole angle of rotation there of 5 pi over 3. Okay. 5 pi over 3. Boom. Done. That's it. That's awesome. You could write that expanded. I think if we're plugging that into my math lab, it's going to look like this. 16 cosine of 5 pi over 3 plus sine, 16 sine of 5 pi over 3i, or 16i sine of 5 pi over 3. Just pay attention to how it's asking you to pop those things in. When possible, we're going to keep them exact, nice numbers here rather than decimals, but in this next one here already, you're going to see that we're not going to have that luxury, okay? So let's go on to number 2 here, and we're going to go ahead and graph it. All right, so I got negative 2 in that x direction, negative 3 in the imaginary direction, in the real direction, in the imaginary. Now I need to find out what r is, but that's not a nice triangle. Sometimes it's even like a 3, 4, 5 or a 5, 12, 13. I got to use Pythagorean Theorem on this one to get r. So the square root of 2 squared plus 3 squared, that's going to give me here, we've got 4 plus 9 is 13. So square root of 13 here. Lovely. Fantastic. Wonderful. All right. I got some notes over here as well. I like to make sure that I didn't make any mistakes. And then I see it in the video later. So I've got r. Awesome. Now, how do I find my angle? Ooh. This one's not so nice, right? So I do know I can use my tangent inverse, right, to find theta. Now, what I'm going to do, I'm going to pull up my emulator here real quick. All right, so I got my emulator here. It doesn't say whether or not we need to do degrees or radians. I think for this one, I'm going to go with degrees just because I feel like it'll be, I'll keep it radians. I'll go crazy. I'm going to go crazy, man. We're going to have a rad time. Radians. All right. So I want to figure out what that angle is. Now, I like to plug everything in positive. So 3 over 2. So that's going to give me my reference angle, right? As if it were in the first quadrant. That's my reference. That's how far it is away from the positive x-axis when we're dealing with an xy coordinate plane. Now, I am dealing with in the third quadrant here. So if I did pi plus that reference, that would give me the angle. So I'm going to add pi. So plus pi, enter. I get 4.124. Okay. So theta, 4.124. And now I have basically everything that I need to write this here in polar form. Okay, so I'm going to have square root of 13 cosine of 4.124 plus square root of 13 times sine of 4.124. Beautiful stuff. And there we have it. We're all set to go here. You could also write this as root 13 cis 4.124 if you want to go shorthand there. But again, if you're adding it into, I think my math lab likes it in the expanded form. Awesome. Wonderful. It was kind of a voice crack. I'm not sure what happened there, but, you know, we're going to roll with it. We're going to roll with it. It's happened a handful of times here. Okay. Now we've got ourselves convert to rectangular form. So we're given polar. We want to convert to rectangular. Once again, I'm going to go ahead and draw this thing up. So if I switch colors here, we'll go blue. We got 150 as our angle. So that's looking like something like this. Why isn't it drawing here? Okay, there we go. So that's 150 degrees. That's going to be a 30-degree reference. There we go. And we've got ourselves a 4 for that radius there. Sorry, sometimes my pen wasn't working right now. I'm not sure why. All right, so if that's a 30-degree reference, that means we're dealing with a 30, 60, 90 triangle here because I got that right angle as well. Across from the 30 is half of that hypotenuse, so that's going to be 2. And this is going to be 2 root 3. So right here, oh, wait, hold up. That's a negative 2 root 3 because I'm going in that negative direction. So in my real direction, I've got negative 2 root 3. And then in my imaginary direction, I got that 2, so that's 2i. So z is equal to negative 2 root 3 plus 2i. If you just got up because you thought that was the end of the period, sit back down. We got more math to do here. All right. I like it. Good stuff. Fantastic. So I drew the triangle. I got my angle. I used that to figure out the rest of the missing pieces of this right triangle. And away we go. But what happens, ladies and gentlemen, when we don't have nice numbers here? We got cosine of 55 and sine 55. My goodness. What the heck is going on here? We're about to find out. I'm going to show you. Come on this journey with me in the land of mathematics. All right. So we got 55 here. I've got 3 here. What could I possibly do to figure things out? Well, I do know, this is A and this is B. I know that A is r cosine theta and B is r sine theta. Okay. So do I have everything that I actually need? I've got my theta. I've got my r, right? So I could actually just do this. 3 cosine of 55 plus 3 sine of 55, and then I'll have that I on there. And I can actually just use my calculator. But because this is given to us in 55 degrees, that's degree mode, we're going to have to switch over this time to degree mode. All right, so I'm in degree mode. Now I can just go ahead and type in 3 cosine of 55, and then I'll do 3 sine of 55 as well. And we've got our 2 coordinates there. We have, luckily I have them written off to the side here. We've got 1.721 plus, and then 2.457i. That's what I get for z. Not too bad. It's honestly not that bad when they're not exact nice values. It's when they are. It really does help to draw that picture, fill in your 30, 60, 90 or 45, 45, 90. But we already had our angle. We had our radius. We're ready to rock and roll. Not too bad. I like it. Fantastic. Let's keep rolling. Oh boy. Time for some operations with complex numbers. If you thought this wasn't already complex enough, about to blow your mind. All right. So we've got z sub 1 being 3 minus 3i, and then z sub 2 being 4 plus 4i. Perform the following operations and graph the complex numbers. So we want to multiply those two. And we can just use our normal straight up foiling distribution techniques here. So I'm going to have, let's see here. We got 12. I don't know why I was about to tell you how to multiply. I figured I could just pause and write that out. So these guys are going to cancel, and I'm going to be left with 12. And then it's minus 12i squared. If you do remember, I squared is -1, so that becomes positive 12. So that's 24. Cool. Awesome. Wonderful. If we're to divide, we can divide these bad boys. Now, what I need to do is I need to rationalize. So we got 4 minus 4i. We got to use the complex conjugate to do so. And when I multiply out, I end up getting, let's see here, this 12 and then the plus 12i squared. That's going to become -12. So those cancel. And I'm left with -24i over 16 plus 16, which is 32, which I can then simplify. Those are both divisible by 8, giving me -3i over 4. Coolio. And then let's also graph both z sub 1 and z sub 2. So I'll do that one in this lighter purpley violet, if you will, color. So I've got 3 and then -3. Boom. There we are. Whoop. And then I'll do the other one. We'll go with, how about, I haven't used orange yet. That sounds wonderful. So I got 4 and then up 4. Boom. Bingo, bango. We're good. We're fantastic. Awesome. Fantastic. Wonderful. And cool. All right. Now, what if I were to graph the other ones, the ones that we multiplied? Well, if I do this one here in blue, that's just 24 in the real direction. So let me give myself some room here, folks, but I'm going to be doing like that until I get to 24. There it is. All right. Now, -3/4 I, if I do that, because it helps, I think, to think of it that way as -3/4 I instead of -3i over 4. Because all I'm going to be doing is going down 3/4 in that I direction there. That one's the green one. Okay? Cool. Awesome. Fantastic. All right. So that was kind of mess. Imagine if we were multiplying multiples, putting a bunch of them together. Like, this could get very messy very quickly. And there's actually a pretty dope theorem that a dude came up with that we're going to explore a little bit more tomorrow or the next year, whenever day it is. Who knows? It could be in a month. I don't know. It is the next lesson. So there's a way to handle this when it's in polar, which is quite convenient. All right, so for some general forms here, children. Sorry, I had to take a little brief pause. You probably didn't even notice it. I don't know why I'm mentioning it. All right, because I just hit pause and that's it. But we had some visitors. So if we have z sub 1 equals that and z sub 2 equals that, then when we multiply the two of them together, our general form would be that we're going to take radius 1 times radius 2 equals, then we'd have cosine of theta sub 1 plus theta sub 2, and then we'd have sine of theta sub 1 plus theta sub 2, and we're taking the sine of that whole angle, okay? And super short form would be r sub 1 times r sub 2 cis, and then theta sub 1 plus theta sub 2. Now with division, I also often like to think about this almost like kind of how like exponents are related. When we're dividing with like bases and exponents, what do we associate with that? Subtraction is brought in. So I'm going to have r sub 1 divided by r sub 2. I'm going to divide the coefficient. And then it'll be cosine of theta sub 1 minus theta sub 2. We're taking the cosine of all that. And then same goes with sine here. Oops. Theta sub 1 plus theta sub 2, right? There we go. And actually, you know, we don't want to forget our wonderful I there. Cool. So again, shortened form. Bingo, bango. We've got it. Awesome. Fantastic. So let's try it. If I've got z times w, and I want to multiply those two together, I would take the two r's, I'd multiply them, and I would end up getting 2 times 3. I'll write it out for this one. And then I'd have cosine, and it'd be 40 plus 70, which is 110. So 40 plus 70, plus sine, and then again 40 plus 70, I. So I'd have 6, and then cosine of 110, sine 110, I. Beautiful. Or 6 cis 110. I'm a fan of that form. I'm a fan of that form right there. Nice and clean, right? Quick, precise. Awesome. How about z divided by w? Well, that'd be 2 divided by 3. And I'm just going to go right to it. Cis. Now I'm going to subtract these. 40 minus 70. 40 minus 70. That's going to give me cis negative 30. Woo! Woo! Or, if we do want to go positive with it, what's a coterminal to negative 30? That'd be positive 330. So I could do that, or we could do 2/3 cis 330. Those would both be acceptable. Or you can expand it out, 2/3 cosine 330 plus sine 330i. I like it. Alrighty, so now let's take a look back at numbers 1 and 2 there. Now that we know this information, right? Well, what would we have to do first in order to use this new formula here, we'll call it right now. So let's get rolling with z sub 1 here. We got 3 minus 3i. So I've already drawn it up, right? 3 in the positive real direction, negative 3 in the imaginary direction. That's a 45, 45, 90 triangle. So we're either dealing with negative 45 or 45 when we convert this here into polar form. And my radius is 3 root 2. So I would have 3, let's see here, we'll do z sub 1 equals 3 root 2. I'm going to go cis, and then we'll do, how about negative 45? I'll keep the number smaller by going negative, right? And then for z sub 2, same kind of idea. I'll draw it up still so we don't make a mistake, but those are both positive, right? So I'm going to have z sub 2 equaling, that's going to be 4 root 2 for my r. And then I'll have cis, and then my angle would be positive 45, okay? And in case you needed help, there's my filled out triangle. 4 in the positive real, 4 in the positive imaginary. Special right triangles of Pythagorean theorem to get that 4 root 2. All right, so now that we have our z sub 1 and our z sub 2, we can go ahead and use what we were just using before. I would multiply, so we would have, let's see here, 3 root 2 times 4 root 2, and then it'd be cis, and then I would add the negative 45 and 45. Cool. And that would be, let's see here, that would give me 0 inside there, crazy. 3 times 4 is 12. Root 2 times root 2 is root 4, which is 2. So 2 times 12 is 24. And then I'd have, I'm going to actually expand that. It's going to be cosine of 0, and then plus 24 sine of 0 I there. And the reason why I did that is because I'm actually going to be able to evaluate cosine of 0 and sine of 0. Cosine of 0 is just 1, so it's going to be 24. Sine of 0 is 0, so my answer is just 24. And look at that. Isn't that what we got up here? We got 24. Oh, there it is. Boom. 24 was our answer. I didn't have to FOIL it all out, cancel things like that. When we get with like more things together, you'll see the benefit a little bit more even, because this one's already kind of a decent amount of work still with the conversion. But when we deal with more complicated things or raising these to a power, this is going to be very, very helpful. All right, now into the division here, and then we're done. Finally, I'm sure Mr. Klein and Mr. Hendrickson are both very happy that they'll be done listening to the wonders of the complex plane here. All right, so we have 3 root 2 divided by 4 root 2. And then we've got cis negative 45 minus 45. Okay. Okay. I like it. So that's going to cancel. I'm going to be left with 3 over 4. Right? And then that's going to be cosine of negative 90 or 270 plus 3 over 4 sine of negative 90 I. And once again, I ended up breaking that up just because I saw that, hey, it's going to be negative 90. That's going to be something that I can evaluate individually. Had I not been able to, if it was like a 37, I would just leave it, okay? Or I'd plug it into my calculator if it asked me to. So if I need to plug it into my calculator, am I going to evaluate it, I'm going to expand it out. So I get, cosine of negative 90. Negative 90 is like 270. That would be 0 for cosine. So this guy's gone. And then I'm going to end up with, let's see here, sine, that'd be negative 1 for that one. So I'd get negative 3 over 4 I. All right. And what did we have when we did this one prior? Whoop. There it is. Circled in green, arrow, green, all the green. Money. Green flannel. Costco. Remember something, this is a 2015. This is a 2015. Shrinks up a little bit. Makes me feel like I have long arms. You know, so there we go. That's it. That's wonderful. Fantastic. Thank you guys for sticking around. You know, America, freedom, rock and roll, Costco, and, of course, Riverdog Jenny on the gram. You know what I'm saying? All right. You guys have a wonderful day.